All right. So today I want to talk about explainability. And this is, again, kind of a split in 2 lectures, similar to what we did for security. The first lecture, we're focusing more on the tools, like what are the techniques. Who here has seen things like SHAP or LIME, so on before? Bunch of you, okay. So it might feel a little bit redundant. We're doing an overview of a number of different techniques and why you might want to use them. And then next lecture, we're talking more about how do you integrate this into a product and what does a user actually need. And that's then also what you're going to do in the last individual homework assignment, where we're giving you a model for a medical application, diabetic retinopathy detection, so it's an eye disease, and you're pretending that you're building a product with this, and you might want to explain this to patients or to nurses who are applying this tool of how it works. So you're going to try to explain a vision model. But let's start. I think I don't need to motivate the need for explainability much, but we're using all these kind of models that we don't quite understand how they work. And this becomes particularly visible if we see adversarial examples. This is a 3D printed object in a kind of airport kind of security scanner thing, where they trick the model specifically to detect this as a rifle. And it's not quite clear why. So we could try to use some explainability technique to figure this out, but without that, there's no chance of us really figuring out why does a model make this mistake. And we've seen many other adversarial examples. We don't know why you can trick a model so easily to, it sounds the same to humans, but the model completely misunderstands this, right, for reasons that we don't quite understand. This is a case I want to talk about a little bit more today as a running example, and Claire will bring back next week when we talk about fairness. This is about recidivism prediction. If you've ever done a machine learning ethics discussion somewhere, this probably came up as an example. The idea here is that originally the idea was that judges are very biased, or maybe very biased. There's lots of examples of where judges might be apply much harsher penalties to certain subpopulations, often based on race, maybe based on gender, maybe based on age. And we wanted to reduce that bias. And why not use machine learning and make objective recommendations based on data? That was kind of the idea. So a lot of people have started looking into this. How can we use past data of people who went to jail, got released, and then got sent back to jail? How often does this happen? Whom does this happen to? And can we predict whether somebody will reoffend? So these are for these discussions when we're about to maybe release somebody on parole, whether we want to decide, are they going to reoffend? So that's what recidivism is. In a lot of states in the US, including Pennsylvania, it's mandatory to use such a tool during sentencing. So in a lot of places, judges are required to put the defendant's data into a tool like this, and it predicts recidivism risk. So up here, the top 3 scores are the main one. Violent recidivism risk, so what's the chance that this person will commit a violent crime in the next 2 years or something like this typically. General recidivism risk, pre-trial release risk, what is the chance that they're fleeing the country or so. And there's a bunch of needs or kind of features back there. So we don't have access to what happens internally. There have been a couple of investigations, we'll talk about this in the future, where people have looked into and discussed the bias in these kind of tools, right? We tried to introduce these tools because judges were biased, and then there was a discussion, maybe these tools are racially biased and disadvantage certain populations. If we want to understand that, whether it's biased, we need to understand how they work. We need to evaluate them. We will talk about, to some degree, about this in the future. But also a judge who makes a decision here potentially needs some information about how they should use this risk factor in their sentencing decision, right? So all they get right now is a number. And why is this specific person judged to have such a high risk, right? We don't really know. It's a black box. And if we want to analyze these models, it's also hard to say, are they fair? However, we could look at these models. This is essentially a decision tree model. There are some researchers that argue that this is equivalent in accuracy to the black box model. This model, I think you can all look at and fully understand. If I were to ask you a question about, is a 25-year-old person, male with 5 prior offenses, likely to reoffend? You could look at that thing and tell me what the outcome is. If I were to ask you, does it matter whether the defendant is black or white? Does it ever matter in this model? You can look at the model and make those decisions, answer those questions, right? You understand that model fully. That's not the case when you train something more complicated. So I have, can I find this quickly? So I've taken some data here. It's training. Wait, this is preparing the data. So this is some public data set that a lot of people look at, that the researchers originally used for discussing bias here. And I'm training a gradient boosting model. And that has 100 decision trees. And to understand what decision happens, I have to look at every single decision tree, at the decisions, multiply this by some factor. I guess you know better how gradient boosting works than me. But it's really hard to really understand what the boundaries are, right? Does this model use a feature? I would have to look at every single tree. If I learn a neural network, so this is a really simple one here, relatively small, I can look at the weights of the model. Doesn't seem really helpful to me, and I suspect it's not very helpful to you, right? So yes, we could look at a model and could look at every single weight if we have access to it, but you couldn't answer the question, what happens to a 25-year-old male with 5 prior convictions? Only if you really do a lot of math on paper, right? And you couldn't answer a simple question of how impactful is race in the decision. This is kind of what explainability does. It wants to tell you, or we want to explain for a specific input, why do we make a specific prediction? Or how does this model in general work? Right? Does it ever use a feature? Which features does it use most? So this is hard. We started often with simple models like decision trees and linear models where we still had some idea of how they worked, but then these days we use large language models with billions of parameters where we have no idea how they work. But we often want at least some idea of what's going on here, and that's what we're talking about mostly today. So, and to some degree you may be required also by law to do this. In the European Union, for some systems, you may need to provide some explanation. Let's not go there. Before I actually talk about techniques, I want to see what you know and do this mini breakout where for 2 systems, I want you to think about how would you debug something like this? How could you try to understand how the model behaves? I have 2 problems here. A vision algorithm that's bad at recognizing stop signs sometimes. And you would like to understand when is it bad, how is it bad, what kind of mistakes does it make, how can we improve it potentially? And this is more tabular data, so college admission system that has a bunch of features for applicants. And somehow it seems to be biased against historically black colleges and universities or graduates of those. Right? It seems to consistently reject those. Is it actually biased? Does it use that in decision making? Is this a problem in our system? Clear what I want you to do? You don't need to write anything down. Just talk to your neighbors about how you would approach this problem. Go. I'm not going to discuss this now. We're doing pretty much the same thing at the end, and I want to hear how things have changed. I want to go through a bunch of different strategies. First of all, there are two. So all these terms are not really clearly defined, but there are two common strategies that we often distinguish. Models that are so simple that we can just look at them. They're called intrinsically interpretable. So you can just look at the model and completely understand, like the recidivism model that I showed you. This is another example of something where the model was essentially turned into a quiz form. So this is a linear model, just with very nice round numbers and a threshold at the end. So these are intuitively understandable, and we can understand how they work. We can answer a lot of questions about them, right? Simple decision trees is the same thing. I've done the same thing here, so I can train a linear in the simple recidivism example, they're actually all of similar accuracy. It doesn't really matter what model we're using. So I can train a linear model. Linear models, we all know from science of how to read them. I can look at the coefficients, and I can see a very big coefficient here is the age, where in contrast race doesn't really matter much in this linear model. The number of juvenile misdemeanor counts doesn't really matter. I can also show this visually, like what are the biggest coefficients here, right? The biggest coefficients that this model uses are the number of priors and the age, and the rest is kind of small in between. This is just training a linear model. If the linear model is just as good as our deep neural network, we can just use it because we can just look at it, we can understand it. Similar for shallow decision trees. I can learn a decision tree. Again, this decision tree is, for this data set, similar accuracy. And this I know how to read, right? Decision trees, if they're getting really deep, it's hard, right? This becomes overwhelming. Multiple forests, like decision forests, become really hard to understand. But simple decision trees, they're fine. So that's intrinsic interpretable. And then for everything else, there's a lot of techniques where we can try after the fact to explain how they work. Right? So I think that's mostly what I already said. This is probably the simplest post hoc explanation that we can provide. It's called a surrogate model. So if we have a complicated model that we don't understand, can we learn a much simpler model for the same problem and use that for an explanation? It won't be perfectly the same model, right? If it would be just as good, I mean, for recidivism, we can get something that's just as good in this example because the problem is so simple. But if it was just as good, why do we use the expensive or hard to understand model in the first place, right? But let's say we have a big model that's hard to understand, and we want it because it's a little bit more accurate. This is the closest approximation that we can get, right? Learn a linear model, learn a decision tree that's inherently interpretable based on that model. So the way that this works is really simple. We select some data set, and I have an implementation here for this too. So here I'm using a neural network model that I trained earlier, and I use it to predict on the training data. So I'm just making predictions based on the training data. So the Y value here, the label, comes from the model, does not come from the original training data. Right? So if the model has learned something systematically different than the training data, I would get the model's prediction here, not the original data prediction. And then I can just learn a decision tree, for example, a really simple decision tree like this that represents kind of what the neural model has hopefully learned. I can also compare, well, the neural network and my decision tree maybe makes positive predictions, then it's not quite the same, right? And The accuracy is kind of similar, but there's a lot of cases where they disagree. So it's not perfect representation, but I have an approximation of that model. Does this make sense? And rather than doing this for the original training data, I can also do this for random data, because it doesn't really matter what the training data does, right? I'm just trying to learn what the original model has learned. So I'm sampling random spaces that they are input to the original model and train a surrogate model on this. This, by the way, really doesn't work in this example because random data in this space doesn't really get me realistic humans. So I have very few samples, if I just randomly sample, that are realistic. I have a lot of people who have like random number of misdemeanors, and like 0 days in jail is probably the most common, or a lot in our data set, but here you just get a random distribution, right? So typically when you do this, you need to put a little bit more effort to create realistic inputs. In this case, this creates a really bad model simply because pretty much everything that I'm sampling says recidivism, because every random person that I'm sampling has so many prior convictions that the model essentially says this is recidivism, right? I have very few random training data of people where the model thinks they will not commit another crime. So this model is not a good representation, but generally, if you put enough effort in here, either use the training data or any realistic data, you don't need labels, right? Or you generate synthetic data that's kind of following the reasonable distribution. This works reasonably well.
I have a question. So what's the difference between this and knowledge distillation?
That's pretty much the same, I would guess.
It's just where there's not having and not
Yes, so the point here is it's a form of distillation or so, but to a specific model that you then can understand, right? So pretty much shallow decision trees, sparse linear models, those are your main choices. What are advantages and disadvantages of this approach for explaining how a model works?
You could distill it into a much simpler model. It kind of exposes the fact that your model is probably over-engineered.
Yeah. So it's also clearly not the accurate prediction, accurate explanation. But we'll see. We will almost never get that, right? They are almost all approximations. Here it's very visible, right? It's just an approximation. And if the model is really complicated, has like very complicated decision boundaries, and we try to approximate this with a linear decision boundary, we lose a lot of things and often probably give fairly inaccurate explanations. But it's maybe closer than nothing, right? It's the closest thing that we can do with relatively simple things. You can do some quality measures to see how much the models agree, to kind of get a sense of how good your approximation is. But yeah, it's not a perfect thing. And if you try to do this to a large language model, you will probably not get any meaningful approximation, right, with a linear model or a simple decision tree. This is also a very useful technique, is just to figure out if I remove access to a feature in the model, how much does the model suffer, essentially. So this is called Permutation Feature Importance. We're still trying to explain the entire model, like how does a model in general work? Does it use a feature, yes or no, not a specific prediction? So the way that this works is I take the model and I take my test data and evaluate accuracy, but before I do this, I take away one feature. So let's say I take away the number of prior convictions. I just take it out of the model or out of the test data, right? I can set it all to 0, or what people typically do is they permutate it, just randomly assign prior convictions so that the model doesn't have any meaningful information, and then see how much accuracy is lower in that resulting model. Does this make sense? So you're essentially trying to figure out how much is a model on average across my entire test data relying on that feature. And what you can see here is prior convictions, the slightly different model, but prior convictions in age are the most important ones. I think I have this also for the same data set here. Right. So in that data set, prior convictions in age are the most important ones. Accuracy drops a lot. Error bars you can get because you can permutate repeatedly. Whereas all the other features have relatively small influences. And there are even some features, I think, if you take them out, accuracy gets a little bit better. I don't know why. But this is often a good first approximation of what is the model looking at in general at all. And you could do this also for a vision model when it shows you just, in general, it often looks in the top left corner of the image. But it's not that useful usually across all inputs there. Does this make sense? The implementation is really straightforward, and you can have libraries that implement this for you, but you can also really implement this yourself very quickly by just, you take your test data, scramble one column, and then just run the result. All right. So now let's say I want to additionally know how so I know age is influential, but I want to know how does age influence predictions. This is where partial dependence plot is a next common thing. The way that this works is I take a model, I take one of my inputs, this is one random person in my data set. I predict whether that person will reoffend, so you get the probability here, something, let's say this was this person here, and now I change their age. I just change their age and make another prediction. And I see the higher I set the age, the lower the model thinks the probability is going to be. And if I reduce the age, it's going to be higher. And now I can do this for every single person in my data set. Right, so I have this, the thin lines is one person each. And I can see what happens if I change the age of that person. And the big red line is the average of all those lines. What this shows me is pretty directly that age has a pretty big influence in thinking recidivism is very high to fairly low, right? The range is pretty big. And then on top of this, I can see how that changes. Like young people are considered less likely to reoffend, more likely. Right, and then the older you get, the less likely the model thinks that you're going to reoffend. Does this make sense? So it's not just, yes, the model uses age, but also this is how the model in general looks at age. And if you have like U-shaped functions or something like this, anything nonlinear, you can also see this in this data set. So I've run this here for all features in this data set. Again, this is pretty easy to run with libraries, or you can implement this yourself. It's not too hard. This is age again, reducing a lot. This is sex. There are only two possible values, but you see on the y-axis that these differences are tiny. So you can see that, I remember, if your sex is 1, I don't remember how this was encoded, probably male, then you're slightly more likely to reoffend, right? Race is also somehow encoded, has minimal differences in this model. What was the other one? Misdemeanor, prior convictions, right? So this is the number of prior convictions. It rises pretty steeply if you have a few prior convictions, and it doesn't matter after 10 or so. It just thinks you're always going to reoffend. Probably not without reason if you have 10 prior convictions. You can also plot this in a 2D space. 3D probably becomes difficult, but this is essentially just a density plot, right, where you can see how prior convictions and age interact, like what's the highest, lowest kind of thing. You still following? So these are all readily available in libraries. And those are, I think to this day, the most common techniques that we have to really understand how a model in general works. I don't think there's a ton more useful things that people have discovered if you want general patterns or general explanations, not for one specific predictions, but what has a model picked up on, what is it looking at. You can translate a number of these things to text and to images where you mask out things and see how much prediction goes down, right? So you could see if I have emails and I block out the sender, does this reduce accuracy, right? This kind of thing in general. How much does a model rely on certain parts of the input? If I block out certain parts of an image, how much does accuracy suffer? Those kind of strategies generalize to other kind of models, but those are the most common ones if you want to understand how the model works in general. I think most of the time, though, we sometimes care about how the model works in general, but most of the time we want to answer questions like, why me, right? Why do you think I will re-offend? So for a specific prediction, why did the model make that prediction, right? So if you have an inherently interpretable model, let's say this, we have a 25-year-old male with 5 prior convictions. What do we tell that person? Does this model think they will re-offend?
Because they have more than 3.
Because what?
They have more than 3 priors.
But they're 25.
Yeah. Let's say 25 and right, but you already made 2 more decisions in that space, right? So, sorry. So the last step was more than 3 prior convictions. But also, I guess sex doesn't matter in this case. But if they were much younger, I guess it still wouldn't matter in this case, right? Is there any way where this matters? No, I guess you could say age doesn't matter. As long as they have 5 prior convictions, we will always say in this model that they will re-offend, right? Independent of age, independent of sex, independent of race. So you can say, essentially, that's the only thing that matters in your case. What if they were, I don't know, 20, male, and had no prior convictions? We would still predict that they would re-offend, but what are we telling them now? Oh, this model uses it. We can talk about whether that model should use it, right? But we want to explain why this model made the decision, right? Not whether it's morally wrong. Oh, this is poor aerodynamics in this chocolate. What would you explain somebody here? A 20-year-old male with no prior convictions. The model says you will re-offend.
If they don't have like big teeth and no priors and they age out, then they'll be good. But right, if they don't offend, essentially pass their
You can also say next year you have 1 free. I don't know that that's particularly useful, right? But now we're in the space where it's actually pretty hard to figure out what is a reasonable explanation here, right? We can say there are 2 factors that were important, your age and your sex, right? We can tell them if you were 1 year older, something else would have happened. Maybe that's helpful, maybe not. If you were of a different sex, something else would have happened. Those are counterfactual explanations. We will get to those where you say, under this different world, right, if something was different, the following things would have happened. You can also say, what were the features that were most influential here? It's sex and age in this case, right? And prior offenses didn't matter in your case. Doesn't matter whether you have 1 or 0 or 5, right? We always would have predicted the same thing. those are potentially useful information. The problem with explanations like these is always, it's really hard to figure out what's a single explanation. This is much more, we'll talk about this more on Wednesday, it's much more social communication. When we talk between humans, we also don't have a really formal language of how we explain that something is causally, this is causing it, because there's usually many, many different factors, and we create selective explanations. We try to create explanations that are maybe nicer to that person, right? Let's say this was a 20-year-old male with 5 prior convictions. We could have just said it's a prior convictions, right? Because do we really need to talk about that the model also would have done this if they had fewer convictions and were not male? Like, we can choose in a lot of ways of how we can explain things. It's not always clear exactly. So let's start with, I think, what the most classic technique in this space are SHAP values. Some of you have seen those before. You get something like this, a force plot here, that essentially tells you what were the features that were speaking for or against a specific outcome. Again, I should show you this with an actual consistent data set, I think, that I had here. Where are my SHAP values? So this is a SHAP force plot here that says, I forgot which, for prior conviction, male, some race, 34 years old. This one says the number of prior convictions were probably the most influential thing that pushed you in the direction of reoffending. Your sex and your race were also not helping, but it only pushed you a little bit into this direction. But the model also considered factors like you're pretty old, you're less likely to reoffend, but this was more important than this in a way, right? So it tries to tell you which features pushed in which direction and how hard they did. This is really annoying to explain how SHAP values work, so I'm not going to try. I'm going to show you how LIME works, which is a simpler version that I can explain. The way that, which one do I try to do? So LIME gives you essentially similar outcomes. This is the same thing, saying for a specific person, which were the features for and against. It's just a different way of rendering the same thing. The way that LIME works is, let's do this here. I have a person here, and let me do it. I think this is easier to explain with this one here. So let's say we have a more complicated decision boundary. This is how the model decides. Everybody on this side is more likely to reoffend. On this side, less likely to reoffend. I have one person here that I want to explain which factors were most important. And I'm doing this in 2 dimensions because that's the only thing that I can show, but in practice this works in higher dimensional spaces. So I'm here, and there's a decision boundary here, right? So I could say, well, if you went in this direction, then something is very important. The intuition behind this is what's driving you toward the closest decision boundary, right? Toward the closest decision boundary, is age or prior arrests more important? And age is closer, so this has a higher effect, in a way, is what this is saying, than prior arrests to get you over the decision boundary. The way that this works is that you learn this linear approximation of the closest decision boundary. So you're trying to figure out not the entire decision boundary, that's what the model does, but you're replacing the model essentially by a linear model, because a linear model we can explain, we can just look at the coefficients. And we don't want a linear model of the entire average of the decision boundary. That would be something like this. But we want a linear model that approximates the closest decision boundary. Does this make sense? The way that this technically works is that similar to surrogate models, you sample all kinds of points and ask what the model would predict, the original model. And then you learn a linear model. But when you do this, you weigh the points that are closer higher. So there are all these gray points here. These are samples in a way, asking what the model predicts. And the bigger things are closer, so we weigh them higher when we learn a linear model. Does this make sense? So the implementation itself is really simple. It's just sampling like a surrogate model in the entire space, weighing these by distance, and then learning a surrogate model, just a linear boundary. And then we can look at the linear boundary, what the coefficients are, and the ones that are the smallest or the biggest are the ones that have the highest influence. Does this make sense? This notebook, by the way, I put in the repository of the class if you want to look at this, play with this. So this is a simple implementation of this rather than my graphics. So there's a person here. There's these dots is where the model has knowledge and sampled things. Again, you see larger dots for closer and smaller dots for further away. And based on this, it learns this decision boundary. I can also now, if I want to, let me try to manipulate this. So this was just a random person. Let's say we use a person that's 72 and has lots of prior convictions, just to have a more interesting data point. The model comes up with very different results. If I run this, like this didn't work, obviously. Okay. So now it's making a prediction for this person here. It's weighing these points in a different way. It actually has little data here. It could also sample in a space that, I think this implementation just samples on the training data points. It could sample in this entire space. But this line now has a different angle than before because it's sampled, or it's decided a different decision boundary closer to this one here. I was hoping that it would learn something very steep around here. It doesn't, and I didn't have time to play with this a little bit more, but that's the idea behind this. Yeah.
In this case, the start is on this side, so it needs to be 0 outcome or 1 outcome. Does the line define the decision boundary or the color?
So the color here is supposed to indicate what the model thinks underneath. And the line is a linear decision boundary that we learn for explanations. Right? So we provide explanations based on the coefficients of that linear decision boundary in a high-dimensional space. Right? So this, again, works for many different dimensions. And then in the end, you just look at the model. These are essentially just factors in the model, coefficients in the model that this has learned. Right, so it's saying H had in this decision boundary, H has a negative weight for where we are. So again, to a large degree, the details don't matter, but I think it's useful to have some sort of intuition of how this works, so that you have some sense of how much you can trust it. Right? Similar to before, there is not just a single explanation, right? You could also say, well, if you were much older or something like this, there's another decision boundary back here. It just tells you to the closest decision boundary, what are the most influential features for this, or which features have the most influence. This becomes fun if you do it visually. So you can take every single pixel of an image as a feature and then see which pixels were the most influential for decision. What's going on here? It grayed out everything that's not very influential. So this one here was trying to classify a husky and thought it was a wolf. It's one of those common shortcut learning things. What do you think happened here? Yeah.
If we're looking at this now,
Right. it's shortcut learning. It looks at the background, right? Because it has learned that snow correlates much more to wolves, right? It doesn't even need to look at the main part of the animal. It just looks at the background, which is obviously something that we don't want to do, right? And if you see this in an explanation, you can often get a sense of what kind of bad things are happening. This is similar. We had this example of the X-ray where the model looked mostly at the text in the corner rather than at the actual cancer because there was leaking labels and information. That becomes very visible in one of these explanations, right? Because you see that in this specific input, and again, this is a specific input. This is not the model in general, right? For this specific input, these pixels were the most influential. I think we had looked for explaining different parts, right? Explaining electric guitar was this. Explaining acoustic guitar was this. Explaining Labrador was this. So I guess this is not really a wrong explanation. I mean, maybe electric guitar and acoustic guitar, where it looked individually, right? But you can see some concepts, and I think if you provide this as an explanation, a human could probably look at this and kind of say, yeah, it makes sense. Or something like this, right? So it's a question of how much you trust it, and that's, I think, one of the main drawbacks here, right? So these local surrogate models like LIME, they're quite easy to build. There's an implementation in the notebook, and there's a model generated for me in a few lines of code, right? It's pretty straightforward. It's not that hard to implement. And it's quite useful for debugging. Not sure that you would show this naturally to an end user or to somebody in front of a judge, like these are the reasons why we convict you, right? But at least for debugging, this is quite useful. LIME is known to be fairly unstable because it relies on specific data points and the closest decision boundary. So you can have minor perturbation or something that's close to another point that gets quite different predictions. SHAP is much more stable. SHAP works in a very similar way, just much more computationally expensive. There's this whole game theory background and then analogies. I'm not going to try to explain it. I think if you think of this conceptually as a better version of LIME, still finding closest decision boundaries, still figuring out which features force the model toward that decision boundary, that's pretty useful. Right, so this is doing feature influence with Shapley values. There's a whole thing here, but this is the thing that practitioners use most commonly. They're nice libraries. You can just run the library easily on a tabular data, on images. It's very few lines of code to get pretty nice results. Any questions? Yeah, this is force plot. This is, again, something for images, kind of saying which pixels were for and against a specific prediction. This is a concept that I like. Not sure that we're using it much in practice. It's an anchor, tells you which inputs were sufficient for making the prediction. So if you have those parts of the input, like we had this with recidivism, if you have more than 3 prior convictions, nothing else matters. Right? So it's essentially giving you a description. In this picture, it would be if you're above, let's say, 8 prior convictions, everything above there is always the same area. Right? You're saying, if I had a decision boundary here, everything above is the same. You can also say, here's an entire area. You're in this area of age between this and prior convictions between this, where we think you're not going to re-offend. This is something that humans often do, kind of describe not the specific result, like you had 9 convictions and were this age, and this is why we did the following thing. It's just saying in general, we have this rule, if you have more than 8 convictions, you're going back to jail. Right? So this kind of thing is something that we communicate. It's not the entire decision boundary, but it's saying for this large part, nothing else matters. So you could say here's a graphical version. If you want to detect the stream locomotive, all these pixels are sufficient. You can change all the other pixels in the image and it would still be detected as a steam locomotive. And I don't have a... There's lots of funny images of this too. There's funny images in the style of you can just swap out the entire background, like you have a dog and then you put it underwater because you can cut out the entire background, right? So you could put this entire steam engine underwater and it would still be detected as a steam engine because those pixels are sufficient. And then I think my last one here are counterfactual explanations. Those are things that we as humans use all the time where we say, well, you were convicted, but if you had one less prior offenses, right, or if you were 5 years older, we would have made the different decision. Right? We communicate in this way. Your loan has been declined. If you had $100 more in your bank account, we would have granted the loan. Right? So essentially what you're doing, you're not doing this formally, but what we can do here is what's the smallest change to the input that would flip the outcome? Does this sound familiar? Adversarial examples, right? So in adversarial examples, we do this to undermine the model. Like, what's the smallest change, like a few pixels around my eyes, that would trick the model? Here we use this in a productive sense to provide explanations. And usually we're not looking for these tricky things where we just try to trick the model, but for more robust changes, right? We want to explain what's the factor here that has rejected your loan. Have you seen Rashomon, the movie? Or the opera, or the book? Somebody who has seen it, what's the plot, or what's the idea? So the book that this is based on, I think in a grove, was a Japanese short story from 1920 something. That was the idea of the unreliable narrator. So the literary device that you have somebody who tells a story that can't be trusted. In the movie and in the short story, you hear about, so a samurai has died, and you hear the story, what has happened from multiple perspectives, multiple witnesses. So you see one person's story, and then you see the story from a different perspective, which kind of overlaps a little bit, but is also different. In the movie, you also hear the story from the medium, or through a medium from the dead samurai. There's lots of versions of this. Like there's a Simpsons story that has the same premise where you see the same story from 3 different perspectives. Lola Rent is a German movie, Lola Runs, that has the same kind of thing that's somewhat well known. The problem is that you can provide many alternative explanations here. Right? Maybe your loan application would have been accepted if you had more money in the account. Sure, that's true. But also if you had lived in a different state, if you had been older, right? So we can think about this, and we have discussed this earlier, right? So if you have a 20-year-old male with no prior offenses, right? You could say if you had been a female, if you had been a little bit older, if you had prior offenses don't matter in this case, right? And not all of these explanations are equally useful in a way. They all would have switched the outcome. Some of those I can control more than others. Like sex changes are kind of difficult. Age changes are very difficult. Number of prior offenses is a little bit late to change that now. I mean, I could increase it probably, but decreasing it would be difficult. If it's money in your bank account, this is something that you can do. It's also potentially something then that you can game. Right, so the way that this works, though, is relatively straightforward. It's just really same with adversarial examples, asking what's the smallest change. Like, I have a point that I want to explain here, And every single point that's across the decision boundary would be a possible explanation, right? So I can say you were 25 and had 5 prior offenses. If you had 10 prior offenses and were 18, we would have said you would reoffend. Here we would have said this, right? So what we're doing is typically the smallest change, but also usually a change where we change the fewest features at the same time. So kind of going straight up or straight to the side is usually preferred than to change 2 things at the same time, right? So predict arrest if you were 3 years younger, predict arrest if you had 3 more prior arrests, but not necessarily this way. You need to combine both at the same time because it just makes the explanation more complicated. And you probably also wouldn't use this one, which is really far away. Right? So usually short distances, but there is no precise way of how to do this in an exact fashion in which one you show. Searching for counterfactuals, you again follow the gradient of a model. If you want, be more efficient. There's a library here that I've used, DICE, that can do this for you. So you put in a specific person here. This is the feature of one person, and it will give you a couple of counterfactuals. So the minus just means nothing has changed. So this is, if you had changed this from 0 to a 4, this from 1 to 0, this from 1 to 0, the outcome would have flipped. So in this case, I think no recidivism. And it produces 3 of these alternatives. You can probably ask for more. You can also implement all of this yourself, but again, most of these things are readily available through libraries. Right? You, again, just follow the gradient or randomly sample in the neighborhood until you find something that you like. All right. Any questions? There's this discussion of counterfactuals are better if they're actionable. So if I can do something about it, right? So there's features that I can change. For example, if I reapply for a loan or if I don't want to get convicted again in the future, those are usually more useful, and making that transparent can also change behavior in an intentional way. It can potentially be used for gaming, right? If we have unreliable features. One more thing that I forgot earlier, k-nearest neighbors is also a very easily explainable technique. Not because there's a model, because there isn't really a model that you can use, but you can also always just say, well, we predict you will reoffend because here's 5 other people that were very similar to you, and they all reoffended, and there was nobody who was similar to you who didn't, right? So this is if you're using K and N, this is very useful often to also explanations like this looks like something else. This is this kind of bird because this thing looks like this in our training data. This looks like this in our training data, right? So people use this to learn features based on top of K and N or similar strategies where you have essentially features that you can understand. All right, quick last part that I want to talk about. So we went through explaining the entire model, like which features generally has the model picked up on, explaining an individual prediction, like we predict you reoffend, why. This is now, there's a couple of techniques about explaining data. Like we used a lot of training data. Which training data was influential for shaping the model? Are there outliers and things like this in there? A lot of this is fairly straightforward, I think. This, I think, is a pretty nice one. Prototypes and criticisms. You essentially cluster your data. The thing that's in the center of the cluster is like your typical training data, your archetypes, your prototypes of things that you're learning. And the criticisms are the outliers. So those are things that also belong to the cluster but are not that similar to something else. And then you can see, so here's an example, prototypes and criticisms for the same dog breed, prototypes, criticism. And then you can think about, are these mislabeled? Or are these outliers and you could create more training data like this? Are they just underrepresented? Right? Is this something that maybe you want to support better? It's really straightforward. You cluster your data, you find the clusters, the center of the cluster is your prototype, the outliers are your criticisms, essentially. This is another fun example, I think. Handwritten digit recognition. It's a really simple thing, but this is how people mostly write numbers. This is also what you get in your labeled data set. Now again, you can ask, are these mislabeled? Are these things that we want to support? Right? All right. And one last thing that I don't want to go into detail too much is, are there any outliers in your training data that influence your decision boundary a lot? Right. So here's a bunch of points. This is the red line is a decision boundary. If we just get rid of this single data point here, the blue line is a decision boundary. Right, so what you're seeing here is that a single data point in a linear regression model completely changes the decision boundary. If I removed any of these points, nothing really would change. Right, so what you can do is train the model on the data set, leaving one data point out at a time or two out at a time, and then see whether any of those really fundamentally change the model. If that happens, maybe you have a poisoning attack, maybe you have a weird outlier, right? So you can decide, is this, maybe I need more data here to decide whether the red line or the blue line is actually the right one. There are some techniques for linear models, you can compute this pretty efficiently. If you have a expensive training job, that's pretty impossible because you're training again on, if you have n data points, you're training n models. Right, this is just really expensive. All right. These all sound really similar. Do you remember what is what? This is the order that we discussed them in the lecture, if that helps. Feature importance is how important is a feature to the model in general. Feature influence is how much did a feature influence this one prediction. Right? So feature importance is a permutation thing where you know this model in general doesn't really look at race. Feature influence is for this prediction, these are the SHAP plots and the LIME plots, right? For this prediction, this feature pushed in this direction, this feature pushed in this direction. An influential instance is the thing at the very end now. Here's a data point in the training data that really biases our model. All right. If you're interested in this, especially on the technical side, this is a book that I can really recommend. It's, I think, the standard book on this right now. It's open access. It goes through all the explanation techniques and also more recent. Actually, I don't think that much has changed in recent years, but this is one that I can recommend in general. It's also well written. So with this, back to you. So we've now talked about all these techniques, and I want you to come back to the two problems that you talked about earlier, and now make a concrete recommendation what you would do here. Which kind of approach would you try for each of these? And this time actually write to Slack. Okay? Have fun.
Christian has my Kit Kats hostage in his office. It's not my fault. No. I was sick, and so I asked my colleague to do me a favor and carry the candy back.
And then somebody forgot to pick it up again.
I had a fever. Anyway, so the point is we have high quality vegan chocolate from Europe where they know how to make chocolate, and so that should be motivating. So We've hit that like sparser attendance part of the semester, which always makes me sad, which I can't really tell you all because you're all here.
First thing is to apply the SHAP analysis and see which features are most important in each case, and then cover one by one the features, drop it, and then see how model performs.
So for the first part, what are you looking at? What inputs?
Features would be inputs, and the performance of the model.
So SHAP and LIME usually work on specific inputs, right? So they explain individual predictions. What prediction are you looking at? Like
probably
specific applications, all applications, some stop signs, all stop signs?
No, I guess we need to look into extreme cases to see which features learn there and see, basically divide the data into cohorts, like normal cases and like more extreme cases, and see SHAP analysis for each
So you would probably have some external input on these are problematic things, right? So in the second one, I think you already have a suspicion that certain universities are the problem. In the other case, you probably need some report from somebody saying, oh, this stop sign wasn't detected, right? And then you can debug that specific input. So you can do additional things. Yes, you can slice the data in different ways and look at prototypes in different parts of the space or something like this. You can sample, but whenever you are doing these techniques, predict individual predictions, explain individual predictions, you need to think about which ones are you looking at, right? And I think what you talked about at the end, by suppressing certain features, there would be a technique that covers the entire model, right? Not individual inputs. You can use SHAP. I didn't show this in the lecture, but you can use SHAP technically also to discuss entire spaces. Then you get something like this. This is similar to feature importance. It shows for all inputs on your training set where are certain things. I don't quite know how to read them, but there's also a plot here where you can. So by doing these individual techniques over and over again, you can also aggregate them. But typically these explanations for individual inputs, you need to think about which inputs. But I think SHAP would probably work for both cases to if you have some suspicious data, to figure out what has the model learned wrong. Yeah.
Okay, for the stop sign, I think we can so there's a lot of stickers in the letter, right? So we can pre-process the image, like getting all those like noises on, like stickers on. So we have to make the like stickers out first, and then rerun OCR to get the letter. So
that would be a way to fix things, right? Yeah. An explanation technique you typically use first to see what's going wrong.
Yeah. So understanding that there is noise like on the letters would be the thing to do for the debug, I think. Yeah.
Would you just detect this manually by looking at the thing and saying, oh, it's probably the sticker, or would you use some technique?
Because like the letter is covered, so like since there should be an error to detect the letter is first, so like it's like it's not stop sign, right? It's just like covered, so like the letter should be like OP or just like O sign, so just like there's error. So yeah.
I don't actually know how much these detectors look for the letters specifically, right? The shape is pretty distinct too. In different countries, they have different letters in it also. But yeah, so you could debug things like how much is this distracted by the stickers versus something else. Did anybody look for any other techniques? Behind you, Claire?
Behind me. Oh.
So for the graduate application system, I think feature influence will be really important because we want to see why exactly the application system is ranking applicants from historically black colleges lower. So, for example, we can see if it's looking at like the age, if there are any patterns among like the age, the race, the majors, for example. of the applicants to see if the algorithm really has some kind of like systemic bias, or if there's a different underlying factor or a confounding factor that's causing these issues.
Right, so you would maybe try to understand how the model works independent of specific inputs, right? Which features does it look to? Partial dependence plots might be quite useful to see how does it look at specific features. Which colleges does it look at? Yeah.
For the graduate application system, I think another method is to use some counterfactual fairness tests, like swapping the institution information of different applicants to measure the casual impacts.
Yes, we'll talk about some of this later. This is very similar to feature importance, right, where you permutate combinations. You maybe don't randomly permutate them, but in very specific ways to test the hypothesis. Yeah. All right. So I think just briefly for generative models, I don't have a lot of extra things. You can do things like chain of thought or prompting, ask a model what it thinks. That's what people mostly do, how reliable that is. Right, you can do all kinds of attention visualization, kind of try to figure out which of the input tokens were most influential. It's usually too expensive because you usually need to sample repeatedly. You can look a little bit at internals of the model. We don't have great explanation techniques, is essentially my summary, but people are working on this right now. So just to summarize for today, there are quite a few different explanation techniques, and don't discount the older, simpler ones like partial dependence plots or this feature importance where we just permutate features. They are really simple techniques that can be quite effective in a lot of cases, even for visual ones. Doesn't always have to be SHAP. Inherently interpretable models are nice if you can use them, so maybe don't build a neural network for this recidivism thing if you don't have to. But there are lots of explanation techniques that don't need any access to the model internals, right? They usually work for any kind of models because you're just probing the model for different predictions. So you're going to see a few of those and play with a few of those in the lab this week. You're going to use probably some of them in the next homework assignment. And on Wednesday, we're talking much more about how to make this usable from an end user perspective.